This is the sections 10.5, the last sections of chapter 10, as well as the last sections for the 230. Right, so areas and lengths in polar coordinates. Now, let's recall. When we're in polar coordinates system, everything will be done completely differently, and any points in the plane will be represented by an ordered pair r in theta. Okay, so directed distance, theta is an angle it makes with the positive x-axis. And so the equations now has to be r in terms of functions of theta. So when you graph the polar equation, we usually have a very fancy graph, right? So it kind of looks something like this, right? So pretty cool. Now, in this section, we will learn how to find the area inside the polar graphs. So, for example, you see if you see the flower like this, and then we might be interested in finding, say, the area of one of these petal. Okay, the petal. So, how are we going to do that? How are we going to find the area inside the polar graph? Now, notice that when we're in the rectangular coordinate system, then when finding the area underneath the curve, right? So the way we do is by doing a slicing. Okay, so all of the technique that we learn by starting with some slicing, vertical slicing. So it's like you cut that into pieces, and each piece now could be like a rectangle, right? So we're gonna find the area of the rectangles. When you add them up, you have the approximations of the area underneath the graph f of x, and then we're gonna increase number of rectangle to infinity. Now, when we are in the polar graph, things differently because of the setup originally is really the pole, and then the polar axis or the positive x-axis. Now, every single point, let's say we find the area inside here, every single point, when you plot points, you actually finding the distance. So that's your r here, there, there, right? So this point, so that's an r. This is the r. So it'll be very difficult when you're trying to find the area using the technique where you do a vertical slicing, right? Because the vertical slicing, basically you're gonna find, like for example, here it can be y coordinate is this point, right? The y coordinate is at this point, give you this distance here, and so that gives you the height of the rectangle. But if you do vertical slicing, then the height of each rectangle is hard to measure because it's gonna be this y coordinate, this point subtract the y coordinate, this point. And don't forget that in the polar graph, you don't have the y coordinates. All you do is the distance from the point to the pole. So this distance we know, but the vertical distance we don't know. And so for that reason, when finding the area of the pole inside the polar graph, we will do a slicing and in the directions, I mean, through the pole. Rather than vertical or horizontal choppings, we will be slice each section through the pole. So like cutting this. And then as we're cutting through this, you see that each of these, if we approximate that, then what happened is each of these will look like something like this, right? So it looks like a pizza, I would say like a small piece of slice. So that would be a sector. It looks like a sector type. And then our goal is to find the area of each sectors, okay? Want to find the area of the sector, we're going to add them up like we did over here, sum up, and then increase it to infinity. Now the question is, how are we going to find the area of each arbitrary sector? Okay. Now, before we get there, do not forget that there is a formula that we calculate the length of an arc. Okay, so the length of an arc in a circle is given by r times theta, where theta given in radians. So what does it mean? So when you have a circle, and again, this is just a review in trig. When you have the circle, okay, and then here's a center, right? It's a center. And let's say if you have this angle right here is theta, that is the radius r. Then the length of the arc, I'm talking about this arc right here. This arc has length r times theta, the radius times this angle. But the angle here, keep in mind, it measures in radian, not degree. Okay, r times theta gives you the length of this arc. Okay, so now using this formula, imagine the area of our polar graph being broken up into infinitely small sectors. So you see, that's what I did up here. I've broken up into infinitely many sectors. Okay, so then you're gonna have each of those here. If we're gonna take one of those tiny things out, you're gonna be like this, right? Then the angle here, okay, the angle here is very small, okay, very small. So I'm gonna call that the delta theta. Delta theta. It's like we call here the small change of x is delta x. This is the small change of the angle. Basically, if you're looking at this, the positive x-axis, you take this angle here, subtract this angle there, then you have the small angle, so that's delta theta. Okay, so that's tiny. Okay, now once you have this angle there, and then this length here from here to here again, it's called r, like the direct distance r. Then this part right here, it's look like just like a sector. I mean the arc on inside the circle. Then this length here is r times the angle. Here's an r. An angle here is delta theta. So you see over here, I have this angle here is d theta or delta theta, actually the same, sometimes delta d theta, but yeah, we use it interchangeably. All right, so here's an r, and so that length here is r times delta theta, d theta. Okay, now because this is extremely small, so technically it's a curve, but you can approximate that with a straight line. So you can think of that as a straight line. Now the reason you think of that is because to calculate the area inside of these sectors, we think of that as like rectangles. Triangles. Okay, so triangle. Because in triangle we have the formula, right? So the area of the triangle is 1/2 base times height, right? So if you drop the height here, right? So this is the 90 degrees angle. So that is your base. So this is your base, and the height is again because it's very small. Then the height here is really approximately the length r. So here's I have the area of each sector here is a triangle. So I'm going to do half base times height. Half base is this length r times d theta or delta theta, and the height is this distance r. Now over here I'm adding the sub I just to mean this is just an arbitrary sectors. When you find the area of the whole regions, we actually have many sectors, sector 1, sector 2, sector 3, 4, 5, 6, 7. So just pick one arbitrary out called the ith sectors. Then to find the area of the whole thing, you're going to sum up the area of these sectors. So that's where you see the summations comes in. Half r times r is r squared times delta theta. So you have half r squared delta theta. Again, we use r sub I. I go from 1 to n. So this part right here is sum up the area of the nth sectors. So let's say divided into 10 of those, then you add them. And then this just give approximations of the area inside that polar graph. And to increase the accuracy, you take the limit and go to infinity. And when you do so, again, limit sum, remember by definition, it is the integral. So it turns into the integral half r squared d theta from alpha to beta. Alpha to beta. Now, don't forget the area is calculated in terms of, for the same momentum, theta. Alpha is the beginning. It's a beginning. It's like a lower ends of an angle, and beta is the upper end. It's again similar to in rectangular form. What you have an integral from a to b. What's a and b? When you do the dx, right? So x is the lowest points of the regions from here to here. So the lowest x values over here is at a, and then the highest x value is at b. Similarly, we have this time is in theta, okay, d theta. So look at this angle. So basically, when you trace this graph here, the first point, I'm looking at this, the very first point, what is the theta? And then when you complete over here, what is the second theta, the largest theta that we have? Okay, so again, when you run from here to here, you're looking at the x lower limits of x here, and then upper limits of these x values. Now, when you find the area inside the polar graph, so let's say that one, this is right here, right? And then let's say here's my pole. Then over here, this point give you what is this angle right here for this point r, what's the theta 1. And then over here at the end, where is the theta 2 here? And those are the alpha and the beta. So setting up the area of the polar inside the polar graph is pretty easy. You just have r squared, the theta. The hardest part perhaps is to figure out the alpha and the beta. Okay, so alpha and beta, that could take a bit of time to figure that out. Now, let's look at the example. Find the area enclosed by R equal to times 1 plus cosine theta. So you're looking at this again and see, I know how to set up according to the formula. It's very easy. It just, the area is the integral of 1/2 r squared. What is r? It's given, okay, r is 2 times 1 plus cosine theta. So you know that it's going to be 2 times 1 plus cosine of theta square the theta. Okay, and then you integrate. The only thing again that is missing, we need to find is the alpha and the beta. So from where to where the theta runs, okay? So now that part is a bit hard because it really depends on what the graph look like. So if you look at these, if you grab this on the graphing calculator, this is what you're gonna see, right? Okay, so that's how the graph look. Now we're gonna find the area inside this regions. Okay, the area is inside. Now, again, if you understand from what we have done in the over here, what we do is the area is set up by doing the slicing through the pole. So that is the pole here. Now, you want to choose a starting point, but normally the starting point you want to be on the x-axis because of this point. What's the angle of this point? It's gonna be 0, right? So starting is 0. So basically, you kind of start over here, and then you slice. Da, 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 da. Okay, so see this slide through. Now think about this. If you start at this point, next, and when you complete and come back to here, my question is the very first point when I start, what is the angle theta? And when you come back to here, what is that final theta angle there? Now, because I'm starting at the original here, so that one on the x-axis, so I think the theta starting will be definitely at 0. Okay, so we at 0. Then when you come back, now normally when you go one complete revolution, it would likely to be 2 pi because when you complete one revolution, but it doesn't have to be. It really depends on what the angle is look like. So perhaps the best way to do is algebraically, of course. You do it algebraically. Now, look at this. This is where I'm starting here. What is the R at this point? The R at this point, you'll notice that from the graph here, you see that this is 1, 2, 3, 4. So he is 4. So I want to figure out what is the angle theta when R is 4. So because this is our equations, right? So basically, I'm setting the R equal 4. So I'm going to find the corresponding thetas there. Right? So R equal 4, or in this case, 2 times 1 plus cosine of theta, right? So that's equal 4. And then what you can do is what you divided by 2. So you have 2 equal 1 plus cosine of theta. And then I subtract 1. Subtract 1, so I have 1 equal cosine of theta. All right, so cosine of what is 1? We can see easily when theta equals 0. Cosine of theta equals 0. What else? What's the next values? Cosine of what is also 0. Cosine of pi 0. No, I'm sorry. Cosine of theta is 1. So cosine of 0 is 1. At pi we got -1, so it's got to be back to 2 pi. All right. So theta go from 0 to 2 pi. Then we have a complete revolution, right? So that means we will have, so that's 0, 2 pi, and that will be our lower and upper limit 0 to 2 pi. Right? So that is our setup here. Now 2 squared, of course, is 4, and then 1 plus cosine theta square. With the complete setup, thing will be, again, it will be easy to integrate. 4 times a half makes 2. This one you got to FOIL 1 plus cosine times 1 plus cosine. You FOIL and you get 1 plus 2 times cosine plus cosine square. Okay, and then we multiply it out to clean up. 2 times 1 is 2. 2 times 2 is 4. Got 4 cosine theta. Now, one thing that we learned earlier that I keep emphasizing, that when you see cosine square, you cannot integrate. You have to use the half angle identities or the power reduction identities. That's a half 1 plus cosine 2 theta here. So you're replacing this with half of 1 plus cosine 2 theta. And from here, we can simplify, cancel the 2. You got 1 here and 2 combined become 3. And then plus 4 cosine plus cosine 2 theta. And from here, we can integrate. Antiderivative 3 is 3 theta. 4 cosine is 4 sine. Cosine 2 theta is sine of 2 theta. Due to chain rule, we multiply 2 when we take the derivative, or we divide it by 2 here when we take the antiderivative. And we're going to plug in 2 pi, subtract, plug in 0. Notice that plug in 2 pi, you got 6 pi from here. But sine of 2 pi, when you plug in here, sine of 4 pi, or plug 0 in, you got 0. Sine 2 pi, sine 4 pi, sine 0. They are all zeros, except the first term when you plug 2 pi in, 6 pi. So we have 6 pi plus 0 minus 0 minus 0 minus 0. And the final answer, of course, become 6 pi as the area inside this polar graph. All right. Next, find the area of the regions inside the polar curve here. Polar curve. Okay. So look at this polar curve. R equal 2 sine of 2 theta. Again, you may want to use the graphing calculator to graph this, and you should see look like a butterfly here, or we call it 4-leaf rose curves. Okay, so that's a 4-leaf rose curve. Now, again, with this area, with this 4-leaf rose curve, they due to the symmetry. We often just find the area of one leaf or one petal, right? And then times 4. Okay, so let's say I'm looking at this one here, and when you cut. So notice that the very first point starting is the pole, then it's come back to the pole. Okay, so again, your setup will definitely have, that one is easy, half of, and then you have the R is 2 sine of 2 theta square d theta. But the alpha and the beta is what you need to find, which in this case, notice that the starting and the ending point is at the pole, since I choose to find the area of one petals only. Okay, I'm going to find the area of this one. Then don't forget that the area of the entire region will need to take that answer times 4. Or maybe before I forget, maybe I should put the 4 out here to remind me whatever the area we got here, we times 4. Now what's alpha and beta? Well, in this case, alpha and beta is the right here, right? So the angle with we at the pole. So at the pole, what is R? R is 0, right? So at the pole, R is 0. So this time I'm going to set the R equals 0 and trying to solve for theta. And if R is 0, you have 2 sine of 2 theta equals 0 divided by 2, we have sine of 2 theta equal 0. All right, then you ask yourself, sine of what is 0? The angle we have is 2 theta. So sine of 0 is 0. Sine of what else? Pi is 0. Sine of 2 pi is 0, 3 pi is 0, and 4 pi is 0. So we have so many. Now, don't forget that 2 theta is equal to this. Then you divide it by 2. You got 0, pi half, pi, 3 pi over 2, 2 pi, and so on and so forth. Now, when theta equals 0, that's corresponding to this pole, right? The first time is we are at the pole. When theta equal pi half, the graph is actually, it's come back to the pole the first time when R equals 0 again, right? So we are here. And then the graph actually, if you graph and calculate, see it's actually run, make another run, and back to the pole. The third time, this is when theta equal pi. So if you're gonna say you want to find the area of these petals down here, then your theta will actually run from pi half to pi. And then you're gonna run again another loop, come back to here at 3 pi over 2, and then the loop come back to original the pole is at 2 pi, right? So it depends on which loop or which pattern we're looking at. If for example, if the graph, if the problem asks you to find the area of this only, right? Then your setup will be, well, it's going to be the same, but you got to be aware that it's not going to be the same as what we have over here, right? So we go from 0 to pi half to pi, and then back to 3 pi over 2. So for this paddle, it's going to be from pi to 3 pi over 2. That's going from pi to 3 pi over 2. Now, since we're looking at the first paddle, so I like the first one. Why? Because it starts with the 0. It's nice. We like 0. So with the 0, it's nice. It makes things easy to calculate from 0 to pi half. Okay, so 0 to pi half. Now, that's the setup. And when you integrate, well, 4 times a half make 2. I'll clean up a little bit. 4 times a half is 2, and then don't forget 2 squared is 4. So I have 4. What did it say? 2, right? So that really turned into 8. 8 integral from 0 to pi half. And I have sine squared to theta. D theta. And do not forget the sine square. What did we say? The square, we have to use power reduction formula or identities to reduce it. That is what it is. Half times 1 minus cosine of twice this. Instead of 2 theta, it becomes 4 theta. D theta. Okay. All right. So from here, I think we can integrate easily. Right. So if you combine, really combine 8 and a half, it will become just 4. I'm going to integrate directly. So antiderivative of 1 will be theta. Antiderivative of cosine is sine. So we have sine of 4 theta there. And we do the reciprocal of 4. So it'll be 1/4 from 0 to pi half. Right? Plug pi half in plus 0 in. I think we got all 0 except the pi half times 4. So your final answer is actually 2 pi as the area of everything inside of this curve. Okay, so 2 pi. Now, the next topic is the area between two polar graphs. Recall, if you have the area between two graphs, right? So we talk about that right here. If you want to find the area between the two, if one is F, the other G, basically you take the area underneath the F, subtract the area underneath the G, you have the area between. And so the formula that we have looks something like fx minus g of x, right? And we say top minus bottom in the case, sometimes right minus left. So that's back to the area between two curves in chapter 6. Now, we actually have very similar scenarios. If you have to find the area inside of one and outside of the other, in this case, so it looked more like you have this one, and then that one, what's the area over here? It's really inside there, but outside of the other graph, okay? So the formula, of course, is the same. You take your subtraction from the one further away, subtract the one closer to the pole, okay? So here's the formula. To find the area between two curves, subtract just like finding the area between Cartesian curves and establish the limits of integrations where the curve cross. So the area now, you see that it's really 1/2 r squared. But now what happened is we have two graphs, okay? So we have two formula, right? So r equal f of theta, and then you have r equal g of theta. We don't call f and g, so let's say this is the graph and there's another graph, right? So we're going to find this area right here. So the one further away, if the pole is here, so that distance is longer, right? So we're gonna probably label that capital R to mean it's bigger. And then the one that's closer we label is lowercase r, right? So technically it's f squared minus g squared, but we're gonna use capital R squared minus a lowercase r squared. It's longer, subtract the shorter, right? So take that distance, we subtract. So this is capital R, and that's a lowercase r. We subtract, you got this, okay, which is this error right here. Okay, so that leads to the formula that you've seen in this slide over here. Okay, half r squared minus r squared alpha to beta. Now alpha and beta in this case will be the intersections like here. Well, if it doesn't intersect, say from A to B, you say that. But if you don't, if they intersect, then you need to calculate or figure out what's the intersection point that gives you A, that gives you B. And similarly, we're gonna have the graph that might intersect, right? So T and here, and that'll be your alpha. And then this angle right here is your beta, right? So at this point and this point. So you may have to find the intersection point, or we're gonna find where the graph the curve crosses. Okay. Now let's look at his example. Find the area of the regions inside the circle are equal 1, but outside the curve are equal 1 minus cosine theta. Okay. Let me do a quick sketch of the graph. Now this is a circle r equal 1, right? So r equal 1 is actually, this one is easy. That one is easy. It's an area of a circle. I need to make it a little bigger. So let's say your center is say over here. So that'll be the pole. We're gonna say the pole is here. The other ones are equal 1 minus cosine theta. What this one look like when theta equals 0. Okay, theta 0, cosine 0 is 1. We are at 0. So again, I'm just want to do it manually. I'm trying to figure out when theta equals 0, cosine 0, 1, 1 minus 1 is 0, so you got 1. So basically the point 1, 0. So we are at the point 1, 0. Where's 1, 0? See, we are this our pole x and positive x-axis, right? Don't forget this circle has radius 1, so he is 1, 0. So when theta equals 0, okay, so over here, the distance r is 1, so actually the intersection is at this place. Okay, so 1, 1, 0 is here. When we at pi half, we have cosine of pi half is 0, so we something not right. Oh, I mean, sorry. Cosine of theta is 1 minus 1, 0, so it's really 0. So that give me the pole. We're at the pole actually. We are the pole. Okay, it's not here. When theta is pi half, then cosine of pi half is 0. Now we have 1, so you have 1 pi half. Notice that pi half is 90 degrees, so it will be here. So I know it's here, and it should go through this one as well due to symmetry. And I should use a calculator to sketch the graph instead of doing manually. But I think just remember as cosine pi is -1, -1 minus will be 2. Cosine of pi is -1. So we have positive 2. If you are looking at this directions, at pi, we are going to units 1, 2, so somewhere over here. Okay, so now we kind of know what the graph is going to look like. Right, so it goes something like this. Okay. So again, you go and calculate, do it instead of doing it by hand, which I'm trying to attempt to do it here. Let's take this out. All right. So we need to find the area of the region inside of the circle, inside of this circle right here. Okay, but it's outside of the curve of this curve, right? It's outside of this. So it's gonna be this side over here. So I'm looking at this region. All right, so that's the region we are looking at. Okay, now you see there's intersection points there, so this is where we need to find first. And the intersection point is, again, like when you're solving system equations in the rectangular form. To find the intersection point, you set the two equations equal to each other. We do the same thing. We set these two equations equal each other's, r equal 1 and r equal 1 minus cosine theta. So that will give us, well, cosine theta has to be 1. Sorry, 0, isn't it? 1 minus 0 is 1. So if cosine theta is 0, cosine theta is 0, and theta is pi half, or 3 pi over 2. Okay, pi half and 3 pi over 2. Now, one things you got to be aware is when you start chopping this, right? I'm talking about slicing method, right? So shouldn't do shading this way. If you're gonna shade these regions, we're gonna shade it through the pole. So where do I start my first line? Okay, so see, it's hard to see. I normally like to start with the horizontal part of x-axis. Why? Because that is to be sure to give me the theta equals 0. And then you can start to okay, so you're gonna be hit this, and actually cannot go the other way because it'll be different. So the best way to do is I'm gonna find the area of this part, like in first quadrants, then I double it. Okay. Otherwise, you probably have to start slicing down here, and then you're gonna move. It's like you move to this side and to that side, right? So move from here to here. So if I start in here, that way I can set up my area formula starting at 0. And then you're gonna move up to here. I'm pretty sure right now it is pi half, right? That's where we found. So that's gonna be from 0 to pi half. And then that's 1/2 r squared minus r squared. Which one is the capital R? The one that's actually further away. Okay, so if you look at this one here, between the purple and the blue actually further from this point is further from the pole than the points on the purple graph. So your capital R is this. So we end up ending up at 1 squared minus a 1 minus cosine of theta squared d theta, right? So that is our setup. Now, by the way, because I choose to go from 0 to the pi half, do not forget that your answer need to double. Okay? Because I modified the area of that part without counting the bottoms. So you need to double it. So I would say there's a 2 times here. And that's equal. Well, that's nice, though. It's going to cancel with that. So now the area is really from 0 to pi half. And 1 squared is 1 minus, before that out, it'll be 1 minus 2 cosine theta plus cosine square theta d theta. And clean up a little bit. You have integral 0 to pi half. 1 minus 1 is 0. I have positive 2 cosine theta minus cosine square. Again, with cosine square, you have to rewrite using the identity. It's half of 1 plus cosine of 2 theta d theta. Now from here, I can certainly integrate. This is the entire derivative cosine is sine 2 sine theta minus 1/2 time. Entire derivative 1 is theta. Of cosine is sine of 2 theta with chain rule times a half. And we go from 0 to pi half. And as you can see, the advantage of using the 0 is when you plug 0 in, you see sine 0, 0, sine 0, they are 0. So if you plug in pi half, you got 2 sine of pi half minus 1/2, that is pi half, plus 1/2 sine of 2 times pi half is pi. Right? And then you plug in 0, they are 0, so I don't need to do any arithmetic there. All I need to do is calculate this. 2 times sine of pi half is 1. And then that will be negative. Multiplied out, that's pi over 4. And that multiplied out is negative 1/4. Inside the pi is 0. Right? So 0. See, that's nice. So after all, the answer is 2 minus pi 4. So that'll be the exact form. You can approximate that in decimal, get the decimal approximations. Right? That finished the first part of 10.5.